So this movie is associated with the second type of worksheet in the course, those in which we went into the WJEC exams, which of course are cited on the front page of the course, and we pulled out appropriate questions. So this first question you can see was taken from the year 2014. That was before the new specs, but the new specs, old specs, pretty much similar, so it's definitely worth pulling a lot of those questions, telling you the unit and the question number as well. Now, things to point out here compared to the first set of worksheets is the first set of worksheets are what I think are important from the university chemistry perspective. The second set of worksheets are based on what the A-level examiners think are important in terms of giving you your A-level exam. Sometimes there will be a lot of similarities, other times a little bit different. Like here, you can see with the atomic structure in my hands, in my worksheet, we started off with the structure of the nucleus, and then we looked at quantitative aspects of hydrogen spectra. We start off here with the qualitative aspects of hydrogen spectra. So without further ado, let's leap into it. So the first two electron energies in hydrogen atom are shown on the diagram, n equals 1, n equals 2, obviously n equals 2 higher than n equals 1. These represent energy levels that an electron is allowed to be in, and it also includes n equals infinity, which is by definition where the electron is no longer anything to do with the hydrogen atom. So anyway, complete the diagram to show energy levels 3, 4 and 5. The point being, of course, first of all, that the 3, 4 and 5 are respectively higher than the 1 and the 2. Second big thing is they're getting closer together, that these energy levels converge, that the difference between them gets smaller. So I'll draw my n equals 3 that's closer to n equals 2 than n equals 2 was to n equals 1, n equals 4 closer still, n equals 5 even closer, and of course this is starting to challenge my ability to draw straight lines close to each other on the computer. Mark with an arrow the energy change corresponding to the ionization energy of hydrogen. Well, the ionization energy that we'll talk about extensively later on in this set of movies is where you take a gaseous atom, in this case hydrogen atom, and remove the electron from it, leaving the 1 plus cation. Now, by definition, for a hydrogen atom, you want the electron to start off in the lowest energy level, so n equals 1, and then when you've ionized it, you've removed it completely, so you've taken it up to the n equals infinity level, thus represented by that pretty little red arrow. Students said the ionization energy of hydrogen calculated using the Balmer series of lines. In which part of the electromagnetic spectrum does Balmer series appear? You either know it or you don't. It appears in the visible. Was the student correct? Well, the ionization energy is where, again, you take an electron that's in the n equals 1 level. Now, the n equals 1 level for the absorption spectrum, so electron going from n is 1 to n is 2, or n equals 1 to n equals 3, or n equals 1 to n equals 4, and so on, are known as the Lyman series. The Balmer series is where you start off with n equals 2. So thus the student was incorrect, said Balmer instead of Lyman. Explain briefly how the lines in the visible atomic emission spectrum of hydrogen are formed and why the lines become closer together at the high frequency end. Well, we start off with the idea that electrons are limited in their possible energy levels. We saw this in question 1. So an electron can have this ground state energy level, or it can have the first excited state, n equals 1 or n equals 2, or the second excited, or the third, or the fourth, and so on excited states. But it can't be in between here and be quite content. It can be in between here in our little picture if it moves between 1 and 2, but it's only there as it's passing from n equals 1 to n equals 2. So electrons can move from one energy level to another, but they can't be in any energy level other than those allowed. Now, when we do an emission spectrum, first of all, we take an electron and we energize it up to higher energy levels. So here's a selection of electrons from 3 different hydrogen atoms, because let's face it, a hydrogen atom only has 1 electron, and one hydrogen atom's electron has been energized up to the n equals 5, another one to the n equals 4, another one to the n equals 3. Now, electrons aren't happy in these really high energy levels, so thus they relax to lower levels by giving out energy. energy. They're going to come down in energy level. This energy that they're giving out is given out as a photon of specific energy, and sometimes those photons correspond to visible light. So thus here in this pretty little picture, we see the electron from n equals 5 went to n equals 2, and if it did that, it would give out purple light. N equals 4 to n equals 2 would give a blue light. N equals 3 to n equals 2, lower energy, so it would give out a sort of lighter blue. And I want you to note, even though that it wasn't required in the questions that I saw in the answer specimen, that if it's going to be visible light, then the electrons are going to end up not at the ground level, but at the n equals 2 level. So the energy gap between n is 5 and 2 is one type of visible light, purple, 4 and 2, blue, 3 and 2, light blue, and so on. Many fireworks contain metal compounds that emit visible light. Colours given by barium, calcium, their wavelength given in the table. Colours seen are a result of emission of light. State how these colours are produced. Well, we already talked about the general idea for emission spectra. So let's take an electron in, for example, barium, and it starts off in its ground state. We give it some energy and we pop it up to its higher energy level there. Okay, now at this point it's unhappy and it wants to give out energy, lose some of that energy and go back down to a nice lower energy level, and of course it gives that out as a photon. There we are. Relax down, and the photon that a barium atom is going to give out is going to be a green one. We see that photon as a light of appropriate color as long as the wavelength of that light falls within the visible spectrum, which is about 400 to 700 nanometers. Table shows bond energies, absorption maxima for hydrogen halides, so HF, HCl, HBr, and HI. The accepted range for wavelengths for the visible spectrum is 400 to 700. Suggest and explain why it's possible that HAT would be a coloured gas. Well, what we see here is that when we're looking at HF, 562 bond energy, nice low wavelength or high energy light absorption, and then we go to HCl, lower energy, higher wavelength, HBr, lower energy, higher wavelength, HI, lower energy, higher wavelength. So what we're seeing here is we're seeing a little trend that as we go down, the wavelength is increasing as the bond energy is presumably decreasing. So what we would expect then for the absorption maxima of HAT, the bond energy would be less than 299, so the absorption maximum would be greater than 400 nanometers. Now, greater than 400 nanometers takes it somewhere into this violet, dark blue, blue part of the spectrum. So this is part of a bigger question, so pretty much you can ignore that first sentence. What's important is that we have a wavelength of 656 nanometers and we want the energy of the radiation. And notice here the energy is in joules, not kilojoules per mole, just joules. So anyway, our standard two relationships, C is lambda times frequency. Pop in the wavelength, lambda 656 nanometers. Again, do not be fooled. Change the nano to 10 times minus 9. I hope as many times as we've done that you will remember to do that when you actually have to do it for real on an exam. So that gives us that for the frequency. And now for the energy, H times F. Pop in the frequency that we just calculated, multiply it by that, and we get this number here, 3.02 times 10 to the minus 19 joules, which is what was required here. Remembering, of course, that is joules per photon, but that's all we needed here. Nice to have that for once, isn't it? How can the Lyman series be used to calculate the ionization energy of hydrogen? Well, we actually discussed this before. Ionization energy is pulling away an electron when that electron is in the ground state. Okay, and the Lyman series are the wavelengths of light whose energies match that needed to remove an electron from n equals 1 from the ground state to higher energies. So n equals 1 up to n equals infinity is removing the electron from the ground state all the way separated from the atom. Now I also wanted to talk about convergence here. So therefore these energies converge towards the n equals infinity, and so while you can't actually see the spectrum of n equals infinity, you can measure the convergence as it goes up, so they're getting closer and closer and closer and closer and closer, so that the final one you see, you can say, that's probably pretty much the ionization energy. Part of the atomic spectrum of hydrogens, we've got frequency going up here. We want longest wavelength. Well, of course, the longer the wavelength, the smaller the frequency, and so therefore A is going to be this one right there. Why do hydrogen atoms emit only certain definite frequency as visible light? Well, we discussed that in question 2, didn't we? And the ionization energy is 2.18 times 10 to the minus 21 kilojoules. Notice that. Calculate the minimum frequency of radiation required to ionize, in other words, pull out that electron in its ground state in seconds to the minus 1. Well, what we've got here is that the energy, 2.18 times 10 to the minus 21 kilojoules, is blah, 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 joules. We don't want that, of course, so we have to convert the kilojoules to joules, 2.18 times 10 to the minus 18 joules. This is a number that you should see many, many, many times before, so it should ring some reassuring recollection for you. And there is the frequency when we pop in the appropriate values.